Okay, then I'd say let's get started, even with this small attendance. Maybe this will evolve or not. Let's see. So hi, everybody. Thanks for joining this session on techniques parameter estimation. So I think I happen to know several of you, but for those who don't know me, my name is Viola Sordini. I am a member of the Virgo collaboration and more broadly active in the LIGO Virgo Kagra network. And so I have the privilege of chairing our session today. So some general rules before we start. Today we have 6 20-minute long talks. We will take the questions after each presentation is done. So if you want to ask questions, you can write them down directly in the Zoom chat. At some point there was a question and answers Q&A box. This is not there anymore, so you just write it in the chat. And then at the end, after the talk, I will call on you so you can voice the question. If you prefer not to speak, please specify it in the chat and I will read your question for you. And you can also just raise your hand and unmute at the end of the talk. Okay, so of course, if there are general questions on the functioning, just let me know. We also, as you've seen, we also have Thankful, who is following she's the technical host and following the session as well. So I'm sure she can help with any special request. And we can start with the first presentation. That's by Vaibhav Tiwari. And the title is What's in a Binary Black Hole's Mass Parameter? So please, Vaibhav, you can share your screen and I'll count on 20 minutes. And then I will tell you 5 minutes left when it's 5 minutes left. Go ahead.
Well, good morning from my side because it's 8 a.m. here. This is a recently finished work where I have focused on the mass distribution of binary black holes as inferred from gravitational wave measurements. Specifically, I will talk about some interesting features we have been observing in the inferred distribution. To begin with, because we understand how a gravitational wave signal produced from the merger of compact object evolves in phase and amplitude, we can use that information to estimate the parameters of the binary that produce that particular signal. And in this slide, I'm listing the parameters that are relevant to binary black holes. They are broadly categorized as the parameters inherent to the binary, such as the masses and spins of the two compact objects. And then there are parameters that are observer dependent, which are in the top section of this list. Not all the parameters are very interesting in terms of astrophysics, but certainly the masses, the spin, and the distance are. All these parameters are estimated in one analysis. On the left-hand side is a 2D slice, which is showing how the parameters are distributed in the component masses. So the primary mass is the heavier of the two masses, and the secondary, the lighter of the two masses. And the plot here shows the estimated masses for the first gravitational wave signal. So once we have made measurements on one observation and the many more which we observe, we can move from the individual aspect to the population aspect of the mass distribution. And to get to this understanding of the population aspect of the mass distribution, we need to address 2 main points. First of all, we have to correct for something called the selection bias, which creeps in because we are biased towards heavier masses because we can see to further, because these masses can be seen to further away distances compared to the lighter mass binaries. So the observed distribution in terms of masses is skewed towards heavier masses and is not the same as the distribution produced in the universe. So we need to correct for the selection bias. And second, we need a model to smooth over individual observations to get an aggregate distribution over the population. And what I've included is an example which is my own methodology I developed a few years back, which uses sum of weighted components to infer the chirp mass, mass ratio, spin, redshift distribution of the binaries. Now we can see actually I use the combination chirp mass and mass ratio to quantify the two component masses. Often the choice is primary mass and mass ratio, where primary is the heavier of the two masses. We basically need two parameters to quantify the two masses. The choice can be made in many different ways. And the more often choice is to use primary mass and mass ratio, which has astrophysical reasons to do. Chirp mass is not a parameter of astrophysical importance, but certainly it is the best measured parameter. But anyway, I mean, we have two parameters to quantify two masses. Here's a distribution which was shared or presented in the recent LVK paper on population analysis. And what is being shown here is how the chirp mass is distributed for the observations we have seen so far. The top plot shows the individual measurement of chirp masses and also an aggregate population level distribution of the observed chirp mass distribution. And on the bottom plot is the inferred astrophysical distribution, which has corrected for the selection effect and has been obtained using this model I shared in the previous slide. And what is interesting is the presence of these several modulations in this mass distribution. There seems to be a presence of a peak around 8 solar mass, around 14, and around 28. And the reason it's interesting is because it's suggesting that a universe is producing binaries with chirp masses that are clustered around a specific mass value. Interesting result because we expect this information to inform on the physical processes that are involved in the production and merger of these binaries. And also kind of surprising because it doesn't fully match with our contemporary understanding of how the mass distribution of binary black holes will look like. So certainly a new result. But before we start making astrophysical implications, we ask the question that how confident are we in the presence of these features in the mass distribution? And the next question we ask is that if I actually infer the primary mass distribution or the total mass distribution, will these features stay? And if they will stay, will the confidence change in those distributions for these particular peaks? It's easy to answer if the whole population is comprised or composed of binaries which are comparable in mass, because features in one mass parameter, either chirp, primary, or total, or any other, will replicate itself in any other mass parameter. And this simply comes from our understanding how we make parameter transformation. But that won't be the case if the mass ratio varies over the mass range. So to quantify or to understand the confidence in the peaks which are showing up in the chirp mass, and also to understand that does this confidence change as we change the mass parameter, I create three models to address this question. I basically create three extensions of this FM model, flexible mixture model, and directly target the two different mass parameters, one of them chirp, the other one primary. The first one is Gaussian mixture model, which is quite flexible at modeling things, and it models the chirp mass and mass ratio using bivariate normals. The second model, instead of modeling on chirp mass, it actually models on the primary mass and mass ratio using bivariate normals. And finally, the third model uses Gaussian mixture to model the primary mass, but it uses a rigid power law to model the power law distribution. And power law is kind of have a tendency to force our inference such that our inference comes out favoring comparable mass binaries. So the first two are very flexible at measuring chirp or primary mass and the mass ratio distribution. The third one, flexible at measuring or inferring the primary mass, but rigid at measuring the mass ratio distribution. So with these models at hand, I infer my chirp mass and primary mass distribution, and this is what it shows up. The top is the chirp mass distribution inferred from the first model. The bottom plot is the primary mass distribution inferred from the third model. And it's very clear, clear enough that the first and the third peak are prominent for both these inferences. but there are substantial changes when at the second peak. So the question arises that first we have different inferences for different mass parameters, and the next natural question is to find the confidence in these peaks. We have 3 inferences for 3 models, and I'm going to calculate confidence in these peaks for each one of the models. To calculate the confidence in the peaks, I ask the question that how easy is it to fit a featureless distribution through these distributions? So what is being shown by the solid line is the median distribution, and the blue band quantifies the uncertainty in our distribution. And the question being asked is that how easy is it to fit a featureless distribution through the band? If for example, if a certain peak is quite curvy and the band is narrow, that will signify that there is a presence of a peak. There's not a featureless feature present at that particular mass location. But if the peak is flatter and the confidence intervals are larger, then our confidence in that feature will be small. For example, the 4th peak is kind of reflecting on that or showing that kind of behavior. So right away we can tell that 4th peak is not that prominent. We can use featureless distribution in many different ways, but the way I choose it is use the broken power law, which has fixed endpoints as shown in these plots. And these endpoints match with the local minima in the median distribution. Then I have to quantify the whole idea of fitting. That how do I fit through these through the orange curve through these bands? And for that to happen, I introduce something called an overdensity. Now, overdensity here, described in this equation down, is a measure that how often my inferred distribution is suggesting a higher density than the orange curve. And I use the word often is because the inferred distribution is actually there are many draws of inferred distribution because the Bayesian analysis, which is shown in this inset in the top plot, each one is a possible distribution at the 3rd peak. The bands are kind of an aggregated over all these individual distributions. So the definition here is the choice is actually based on the number of inferred distributions that have a higher value than the orange curve, the featureless distribution. And it is calculated for each mass value. M is the mass value. So if it's 1, then we can say all the inferred distribution has a higher density than the orange curve, and there is presence of a clear overdensity. And if this is 0.5, then we can say half of them are above the orange curve, half of them are below the orange curve, similar like the 4th peak, and we don't have much more confidence in the presence of a peak. So with FM defined, with orange curve defined in terms of the endpoints, the next thing is to vary the exponents of the individual segments in the broken power law, such that FM is minimized throughout the mass range, and it gives a kind of a best fit. So fixed points are fixed for the orange curve. The exponents are varied so that FM is minimized throughout the mass range, and then I treat each peak individually and find out at what mass value F is the highest, or I calculate the F highest for the best fit orange curve for each of the individual peaks. FM is changing throughout the mass range. So certainly there will be one mass value which will be the highest for a particular segment, mass segment in this broken power law. And with the 3 models I have, for each model I have 4 segments, and for each segment I have 1 F highest value for the best corresponding to the best fit orange curve. And then I flip the question, and to quantify the confidence in the peak, I ask that given the orange curve as the underlying distribution, how often just from fluctuations can I generate F highest value? Now, universe has given us only one realization, but we can do simulations and create many many realizations. So with orange curve as the underlying distribution, I create very comparable methodology, doing exactly the same as what I did for the astrophysical inference of the astrophysical distribution, but using orange as the underlying distribution. I asked the question, how often the stimulated population can create the F highest I've been observing in the astrophysical distribution. And here's a summary of the whole comparison. Basically, I performed 1,000 simulations, compiled the statistics for each peak, find the F highest corresponding to each simulation, compile the statistics, and compare my statistics with the F highest of obtained for the blue curves. So just looking at the top 3 lines of this table, the F highest for the blue distribution or the astrophysical distribution is 1 for the first peak, and none of the simulation actually produced a F highest value of 1, which means that there's not a possibility in terms of fluctuation that the orange curve can produce the peak observed in the first segment. The second peak shows up has the F highest value of 0.98 in the astrophysical distribution. But when I do simulation, I see that only 6% of the simulation result in F highest of 0.98, which reflects or signifies that even second peak is kind of significant. Similarly, the third peak is also can be concluded as significant, but the fourth peak is not. And we can draw conclusions for the other 2 models also. All in all, the summary is on the right-hand side of this slide, where the main points are that the first and the third peaks in the mass distribution are significant, but actually there's something going on at the second peak. The second peak is significant in the chirp mass distribution, but it is not significant in the primary mass distribution, as can be seen from the second line in the table. It becomes slightly more significant in the second model for the third model because of the change in the way we model the mass ratio distribution. We can understand why this is happening.
Sorry to interrupt, you have 5 minutes left.
Okay. To understand why this is happening, I'm including this plot here, which shows that actually there is a unique correlation between the primary mass and the mass ratio, such that even though the primary is distributed in a wide range, the combination which results in chirp mass is distributed in a narrow chirp mass range, around 14 solar mass. And this is interesting because chirp mass is not a parameter of astrophysical importance. And this unique correlation is acting in such a way that chirp mass measurements are all very packed up, but the primary mass is spread out for the second peak, and that reflects in our inferences on the confidence in the peaks. And I'll go a little bit forward and show that this mass ratio distribution, which occurs at the second peak, is complemented in an interesting way by the mass ratio distribution seen at the third peak and the first peak. And on the right-hand side is showing how the mass ratio varies with the chirp mass. The second peak is asymmetrical. These mass ratios, the binaries are asymmetrical masses, but the third peak shows up the most symmetry. That means the masses are most comparable at the third peak. For the first peak, if I include GW19-14, which is the most asymmetrically measured binary, then I see actually that the first peak shows the most asymmetry in masses. And we see a kind of a trend that happens from third peak to the second peak, the first peak. And the natural question that arises here is that I have the second peak, which is confident in chirp mass, but not in the primary mass, where chirp mass is a parameter not of astrophysical importance, but primary mass is. Similarly, there's a trend, still a preliminary evidence. There's a trend in the mass ratio that shows up in the chirp mass, but does not show up in the prime mass distribution. And thus the title of this talk, what's in the binary black hole mass distribution, mass parameter. I think I've run out of time, so I'll stop here and take any questions you may have.
Thanks a lot. No, you were perfectly on time. You still had 2 minutes, but we can take those for questions. So I don't see any question in the chat. Anyone has questions for Vaibhav? You can raise your hand in Zoom. And while you think, let me start. I had a question on your slide 6 in the general procedure. So you have this choice of, big bins, like I think you call them segments in the mass structure to make this analysis. And I was wondering, does anything depend on this choice? Any, conclusion, or you tried, it was just a reasonable choice, or you tried to, I don't know, optimize it, or is there any reason behind, or would it change if you change it?
Yeah, that's a very good question. Of course, our implication will depend on the choice, but I haven't tested thoroughly how much, but my belief is not much, because all I'm trying to do is focus on the peak and trying to fit a power law through between 2 minimas, and just looking how well can I fit a straight line through those endpoints. It's very hard to fit a straight line through these minimas between 4 and 10. It has to be a curved thing there. So I think it's a reasonable analysis in terms of confidence.
Okay, I understand. And since I don't see any other hand, I take the chance of asking a second question. I think these kind of studies are very important, because in some cases we are kind of model dependent. And so I just wanted your general feeling. So do you think the LBK, do you think we are doing a good job in controlling the biases of our model assumptions? For example, do you suggest in the future we might do this kind of study and associate, I don't know, a kind of p-value or significance to our substructures? And how do you see this evolving with more statistics? Will it be harder, or will it be easier because we have less fluctuations?
Yes, I mean, statistical uncertainty will certainly, the bands will go down because we'll have more observation. The blue band won't be as thick. But it may happen that the peak, the second peak, which is looks very narrowly placed around 14 instead of mass distribution, may spread out because there'll be observations farther away from the peak. How it impacts, we will only know after we add more observation. There's no way really to tell beforehand. No model is a good model eventually. We just do our best to suppress the the systematics that is creeping in. Here, what is interesting, I find, is that there is a systematics in terms of the chosen mass parameter, which is not the usual thing we talk about. And there's something I would like to keep in my attention as we add more observations.
Yes, no, I think that's a good point. Okay, well, thanks a lot. I don't see any other hand. If I miss your hands, okay, just write on the chat. But if there are no other questions, thanks again.
Thank you
for the nice presentation and for being on time. So we can move to the second talk. This is by Charlie Hoy on inferring the properties of LISA sources. So Charlie, you can share your screen. Okay, I see you. And
amazing, thank you. So firstly, thank you very much for giving me the opportunity to present today, and it's a pleasure to talk to you all this morning. So today I'm going to talk about a project that myself and Laura, Nuttall and others at Portsmouth have been working on, where we're trying to infer the properties of LISA sources from gravitational wave observations. Now, obviously LISA isn't flying at the moment, so not real gravitational wave observations, unfortunately. But firstly, what do I mean when I say inferring the properties? So when I say inferring the properties, I of course mean performing Bayesian inference, and therefore solving Bayes' theorem. So if we consider, for example, a binary black hole system, Bayes' theorem tells us what the posterior probability is, which is essentially the probability that the binary has a certain set of parameters lambda. So for example, masses 10 and 5 solar masses, for example. What's the probability of the binary having those parameters given the data that we've observed and our gravitational wave model M? And this is simply equal to the product of the likelihood, which is just the probability of the data given the binary parameters lambda in the model M, multiplied by our prior, which is our prior belief of how likely those those binary parameters are. divided by the evidence, which is just essentially a normalization constant. So our prior can be anything we want it to be. We can assume agnostic priors, for example, and assume that all binary parameters are equally likely. So, for example, we can say if we were considering them black hole masses, we can say that black hole masses are all equally likely. We're more likely to see a mass of 10 as 100, for example. Or leading on from Vaibhav's presentation before, we can use a more astrophysical prior and say there could be a peak at various values in the mass distribution. This is up to us as to what we want to choose. But in essence, when I say inferring the properties, I basically mean solving Bayes' theorem to estimate this posterior distribution. So therefore, what do I mean when I say of LISA sources? So this is a really nice plot that's taken from the LISA L3 mission proposal. And this shows some of the sources that we'll be sensitive to with LISA. So I'll just highlight a few of them. So we see MREs in the bottom part of this plot. So MREs are the extreme mass ratio in spirals. So here, this will be, for example, binaries with mass ratios of around 1,000, well, anywhere between 100 and 1,000, let's say. So very unlike what we've seen before. And we also have LIGO type binary black holes, or LIGO-Virgo-Cagra type black holes. So these are stellar mass black holes that we'll see significantly earlier than the LBK, and we'll hopefully be able to predict when they'll merge in the LBK band, which would be really interesting. So you can see those in the far right-hand plot here. And for interest of this talk, we have massive black hole binaries, which is shown by this orange to black curve here. And you can see that they merge at different frequencies depending on the total mass of the system. So when you're about 10 to the 5 solar masses, you see it merging at around 10 to the minus 1 hertz, and 10 to the 7 around 10 to the minus 3 hertz. Now, massive black hole binaries are astrophysically important or interesting points of view because they'll provide sort of like a unique information on galaxy formation, and they could help to understand, for example, the growth of massive black holes in general. And as they're at a high mass, they'll be detected at much larger redshifts, and so they can actually be a really interesting tool to test cosmological parameters as well, which is really interesting. So let me put this all together. What do I mean when I say inferring the properties of LISA sources? So the aim of our project was to essentially develop the tools needed to infer the sources of, to infer the properties using Bayes' theorem of LISA sources from gravitational wave observations. Now, as I primarily come from an LBK background, my natural starting point was to use the Bayesian inference library, or BILBI, as our starting point. So the Bayesian inference library aims to provide a user-friendly interface to perform parameter estimation. And it was written by Ashton et al. Back in 2019. And it's, as I mentioned, or as I alluded to, it's commonly used by the LBK to perform Bayesian inference on stellar mass black hole binaries. So this is what's shown in the bottom right plot here, which is taken from the third gravitational wave catalog. So what this is a plot of the posterior distribution of the total mass and mass ratio for all of the observations that the LBK has seen in the O3b observing run. And each of these contours show the 90% credible interval of that posterior distribution on this 2D slice. And the reason I'm showing this is to highlight that BILBI was used to generate these posterior distributions for all of these contours or posterior distributions that we've seen, for all these posterior distributions for the gravitational wave observations that we've seen so far. So it's got a proven track record for performing Bayesian inference on gravitational wave signals. So it was a really natural starting point for us to extend to be able to use LISA, or to be able to consider LISA sources with BILBI. Now, one of the issues with performing Bayesian inference of LISA is the gravitational wave model. So the gravitational wave model is required in order to evaluate the likelihood. So that's what's shown here. The likelihood is simply the exponential of -1/2 multiplied by the inner product of the data minus our predicted gravitational wave at a certain set of parameters, lambda. So we need this gravitational wave model to tell us what the gravitational wave will look like for a given set of binary parameters, lambda, as seen in the gravitational wave detector. Now with LISA, it's a little bit more tricky than with the LVK, because we're going to have unequal arm lengths and time varying arm lengths, primarily because this is a spaceborne detector or observatory. So the different sides of the detector are going to be moving around as thrusters are fired and all this sort of stuff. So the arm lengths will be unequal, which means that the laser will experience different time delays in the two arms, and hence will not directly cancel each other at the detector. And the larger the difference, the larger the magnitude of laser frequency fluctuations affecting the detector response, and so on and so forth. So it really does impact our gravitational wave model. But one of the key ideas that was developed a while ago was to use time delay interferometry. So time delay interferometry technically involves time shifting and linearly combining independent Doppler measurements. But for interest of this talk, it essentially just forms sort of like an equivalent equal arm interferometer, which is much easier to deal with. Now, in this sort of TDI representation, the laser noise is significantly suppressed, and we're much more sensitive to gravitational waves and gravitational wave observations. So it makes sense to do our analysis in this TDI framework. So in this TDI framework, there are a few variables or channels that can be formed. Some of them are the X, Y, and Z channels. But an issue with the X, Y, and Z channels is the noise is correlated, so not ideal. So what we do is we linearly combine those X, Y, and Z channels and form what's known as A, E, and T channels, which we'll discuss in this work. So the A, E, and T channels have uncorrelated noise. And what's really quite interesting is that the T channel is not sensitive to gravitational wave observations at low frequency. So I'm not going to show any of the plots and discuss the T channel too much in this talk. I'm just going to focus on the A and E channels. But when we perform Bayesian inference, we do take into account all the three A, E, and T channels. So now we have our gravitational wave model, we have our data. How do we actually perform the Bayesian inference? Well, as I alluded to, we do have a gravitational wave model, and that's based on the BBHX package. So the BBHX package was developed by Katz et al. And it essentially is a wrapper for IMR phenom D and IMR phenom HM, which are commonly used waveforms used by the LVK. And this package, BBHX, essentially generates gravitational wave polarizations and projects them onto LISA to form an arm response. And it then generates the waveforms in the TDI channels. So here is an example of a massive black hole binary, as seen in the channel A and the channel E. And there are several things to note here. First of which is that the duration is much longer than what we're used to seeing by LVK observations. So here, for example, we're seeing that the in-spiral or merger ring down part is of the order of 1,000 seconds or so, if I'm doing that conversion correctly. So it is significantly longer than what we're used to seeing with LVK observations because the masses are so much larger. So now that we can generate waveforms in this TDI framework and we can access data in this TDI framework, we have everything we need to perform Bayesian inference. So firstly, what we did, as with any analysis, is we started with a zero noise injection. So we injected a IMR phenom D waveform into these TDI channels using the BBHX package. And you can see on the right-hand side is the inferred posterior distribution. So along the leading diagonals are the marginalized 1D posteriors for left chirp mass, then mass ratio, then distance, then the two spins. And on the 2D panels show the 2D correlations in those parameters. Now, this was performed with full nested sampling with the Dynasty sampler. And this was via the parallelized version of Bilby, the parallel Bilby code, which again is readily used by the LVK for observations and things. Now, because the corner plot was quite large, I only show some of the parameters here. But in general, we found that the injected values or the posteriors aligned with the injected values really quite nicely. We see that the distance doesn't peak at the injected value. I suspect this is because we're only considering the aligned spin 2-2 mode, so we're unable to break the distance inclination degeneracy. So we see a slight shift there. Now, this is expensive.
Sorry to interrupt. You have 5 minutes left.
Oh, thank you. This was expensive. We're performed on 400 CPUs, and it took around 7 days. So it is expensive. The next thing we wanted to do was analyze real or idealized instrumental noise, so Gaussian noise. So thankfully, the LISA consortium have released multiple data challenges to tackle unsolved problems and to test future algorithms. So one of those was the Sangria blind data challenge, which I show the data here in the TDI channel X, and this is a year's worth of data. And there was an undisclosed number of massive black hole binaries in here, and we wanted to analyze a few of them and see how our algorithm works for this case. So rather than showing another corner plot, I decided this time to show you the actual gravitational wave in these channels. So in gray, you can see the data. You can see our median gravitational wave that we inferred through our Bayesian inference in blue. And you can see that it very nicely matches the data, and you can see that it really nicely picks up the gravitational wave, which is really good to see in the A and E channels. Now, I did say this was a blind data challenge, and that is true. But subsequently, the LISA consortium did release the injected values. So I showed the true values, the injected values in orange here, and you can see that the blue and orange really nicely line up with one another, which is really nice to see. So we were able to recover the properties to a high accuracy when analyzing idealized noise. So as a final test case, we wanted to analyze realistic instrumental noise. So again, thankfully, the LISA consortium have released another data challenge known as SPRITZ, which includes realistic noise for the first time. So that's what's shown here. This is a spectrogram in the TDI channel X. Oh, sorry, TDI channel A. And what we did is we injected our own signal in the middle of this SPRITZ data. So this data was 31 days in total of realistic noise. And it did include 2 loud massive black hole binaries, one at the start and one at the end. Now, the signal at the end had an SNR of around 2000 and did last for 31 days. So when we injected our signal, which was around 7 days before that merger, there will be a little bit of overlap. But I don't think it will cause too much of an issue. Ideally, I would have just injected into raw realistic noise without that second massive black hole binary, but I don't know how to create realistic instrumental noise at the time being. So we just used what was available to us. And on the right, again, I show a corner plot and show the inferred posteriors against the injected values. And you can see, again, we do pretty well. You see that the posteriors no longer peak at the injected values, which is somewhat expected. But what's really nice is that the injected values do lie within the 90% credible intervals, which is really nice to see. So finally, I just wanted to say that I've mentioned that it is expensive to run this. For the zero noise injection, we were looking at around 7 days and 400 CPUs when we're only using IMUF and OMD, so an aligned spin 2-2 only model. And therefore, if we include higher modes or precession even, this will become unfeasible. So are there ways of reducing the runtime? Well, one of the ways is to use the Heterodyne likelihood. So this is a way of reducing the overall runtime of parameter estimation and likelihood evaluation by using what's known as a fiducial waveform that looks like the true gravitational wave signal. So here I show the difference in log likelihood between the full log likelihood and the heterodyne on the y-axis and the full log likelihood on the x-axis for some random points that I chose. And you can see that the difference between the log likelihood and the heterodyne likelihood is very small compared to the actual likelihood. So it seems a natural extension to be able to use the heterodyne likelihood to form Bayesian inference. And this is what was used by, for example, Connor Weaving and et al. In their paper, which was released a few weeks ago. And in Bilby, this is very easy to do. It's just a very easy setting to change. So we did run with the heterodyne likelihood, and we found that the P was around 20 times faster. One issue that we're currently investigating is how dependent is our parameter estimation on that choice of the fiducial waveform. If our fiducial waveform wasn't very good, let's say, and it didn't look like the true gravitational wave signal, how much would that bias our gravitational wave inference? We're currently investigating that, but it does look like a promising avenue to massively reduce over runtime. So then that brings me to my conclusions. So in general, we have modified Bilby to perform Bayesian inference with LISA sources and run on LISA data. We've demonstrated that nested sampling can be performed within a realistic time frame, although it is expensive. And the Hetchdine likelihood is a promising avenue to speed up the inference, but we do need to study how dependent we are on those fiducial parameters. And this complements work done by Connor et al. And as well as other codes, because it's really nice to have multiple independent implementations to check for systematics and RPE codes and things. So yeah, thank you very much. If you have any questions,
thanks a lot. So I don't see any question in the chat. Please raise your hand if you have questions. Meanwhile, I'll ask mine. I take all the privileges. So the first is very technical. So you talk about this TDI representation or framework. So you have a change of variables in the end. And I didn't get exactly. So this at the beginning, I had the impression this was happening upstream of Bilby. And then you're telling Bilby this is just a usual interferometer with fixed arm length. But then you talked about development in Bilby. So I just wanted to understand exactly. So did you have to make some development in the Bilby code specific for LISA, or this was happening?
Yes. So sorry if I wasn't clear. So the TDI representation is just a post-processing step, which is done outside of Bilby. So the data will come down in this TDI representation, as far as I understand. So what we had to do in Bilby was change sort of like the waveform generator to use this BBHX package and sort of code up how to consider this triangle interferometer and all this sort of stuff. But we didn't have to worry about the TDI channels themselves because the waveform package returns the waveforms in this representation, and the data will be given to us in this TDI representation, as far as I understand.
Okay, I see. Sorry, then I misunderstood. Good. So it's a post-processing, and since I still don't see any hand, but please complain if I'm missing your hands. So for long signals, as you know, in the LVK, we, for example, we use this ROQ models for long waveforms. I've heard about multi-band usage of Bayesian inference. So since you talk about very long signals, do you think these solutions might be of interest here as well?
Yes, so that's something I really want to look into, is the development of ROQs here, because this is, with IMOF and OMD, it should be relatively simple to be able to produce an ROQ, especially for these really high masses. So it is something that I really want to look into, and it will hopefully speed up the inference quite significantly as well. When it comes to sort of like the multi-band in likelihood, which is developed by Soichiro Morisaki, I did try running on that. But I found we didn't get significant improvements. In that case, the main improvement came with the Hetchdine likelihood. But the ROQs, I think, is a promising avenue, which I will hopefully look into at some point. But as of right now, there is only this, as far as I understand it, this BBHX package, which does this antenna response for LISA, which is crucial.
Okay, sure. Yeah, I understand. Okay, thank you, Lara. Okay, we are done with our, if there are no other questions, then I thank you again.
Thank you very much.
Thank you. I'm already quite a bit late on the session, sorry about that. So the next speaker is Davide Gerosa with the talk on, the talk is eccentricity, spin, precession, and gravitational wave signals that are too short. So, okay, great. I already see your slide, so you go ahead.
All right, perfect. Thanks all for joining. So this is a piece of work done in collaboration with Isobel, Romero-Shaw, and Nick Loutrel. Where we asked the question, we were motivated by 1905-21 and started investigating the genesis between eccentricity and spin precession in the context of the length of the signal, as I'll try to show today. All right, so just for a brief overview, I like to think that the best in gravitational wave astronomy is yet to come. We've got 100 events, 100 surprises so far, and these numbers will become thousands in 5 years or so, millions probably in 20 to 30 years with third generation detectors. And as you increase the number of events, there are two things that are going to happen. A larger statistics means details emerging at the population level, like we were half an hour ago or so, but also more events means the rare outliers will start to show up, and often in rare events in corners of the parameter space, they are very constraining in terms of both astrophysics and possibly fundamental physics. Right, so let's try to go through the black hole property checklist. So black holes are simple objects in GR, so we don't have that many things, that many parameters we can take out of them. We've got the masses, and I would say that's done, quoted. Of course, the precision will go down, but so masses are one of the things that we started to measure and constrain from the very beginning. There's some spin information in some of the events. We definitely know that some of the events that we see are not compatible with both black holes being, say, non-spinning. And then things becomes harder and harder to address because they have weaker effects on the signal. So spin effects also cause orbital plane and spin precession, which is, I put a yellow question mark here. That's my personal view, and it's unclear whether we've seen it for real or not. The next thing that one could go after is eccentricity in the black hole binaries, and I put a red cross here because I think that we are not there, at least not in any conclusive form. And so both orbital plane, both spin precession and eccentricity are very constraining, or are believed to be very constraining in terms of, say, astrophysical formation channels, because you've got to form eccentric sources if they are there, possibly with some dynamics in dense stellar environments. So eccentricity and spin precession are the next thing we want to measure in gravitational wave astronomy. And maybe, and it's debated, but we might be almost there. And well, hopefully HO4 will throw some surprises at us once more. So the question we want to ask here is, can we tell the two effects apart? Right. So there are some funny guys already in this business. So, and let me try to go through them quickly. So there's one event, 2001-29, that has been claimed to have strong evidence of spin precession, but that's kind of muddy in a sense that it depends on the waveform model that you use. Arguably, the more accurate waveform model does find spin precession, which is good, but it was also an event with a big glitch on top, and glitch removal has been questioned, at least in some papers. There are a couple of events, these three that I listed, where there was at least one paper claiming tentative evidence for eccentricity there, though it was analyzed with a template that didn't include spin precession. The most emblematic case in this is 1905-21, where it's really a pick your favorite scenario. So the flagship LVK analysis highlighted precession effects, but things kind of have changed and the evidence has gone down in subsequent data releases. Soon after the LVK publication, at least two, three papers claim eccentricity effects in the events. There are even studies claiming it's even hyperbolic, or that they are not even black holes, but more exotic objects. Now, 1905-21, crucially, is short. So these are the output of the detector, and there are basically 4 cycles, whatever. 4 of them are from the merger of the black hole. So there's basically 1 in spiral cycles. And both effects, eccentricity and spin precession, really build up during the in-spiral. So it's really a case, or it could be a case, where you have one ups and one cycle that you can fit almost whatever you want in there. So it's actually, I like to think it as a matter of time scale. So spin precession has a typical period in which the spins go around, and eccentricity has time scale related to the apastron and periastron passages. So if your signal is shorter than this typical time scale, it's going to be hard to tell the two apart. Right. So this is the intuition, which is perhaps obvious, but what we are trying to do in this paper is to try and quantify, right? So how the distinguishability between precession and eccentricity depends on the number of cycles in band. So that's the goal here. Right. So the context is, again, parameter estimation, like we are all doing in this session. In this specific case, performing parameter estimation with both spin precession and eccentricity, it's currently beyond reach. So we're not there yet. We know people have done, and we know how to do injection recovery campaigns where spin precession is included, but the orbits are quasi-circular. So there are efficient waveform templates for that. And people have also been running analysis with aligned spins, but including some effects of orbital eccentricity. So in this context, we approach the problem as follows. So we perform 3 series of injections, one where the black holes are eccentric and non-spinning, one when they are eccentric but with aligned spins, and a third one where black holes are on quasi-circular orbits but with precessing spins. Now, for each of these systems, we try and recover the signal with both an eccentric template with spin aligned and eccentric templates, as well as a precessing templates on assuming the quasi-circular orbit. So for each of these series, we try and recover with both and compute bias factors to claim distinguishability, whether the correct model or so is preferred or not. Right, so this is the context. Now, it's important to clarify a little bit what we mean by eccentricity. So, well, there are important issues in general relativity in general on how to define eccentricity, because orbits are not closed because of the in-spiral. Even if you let these issues aside for a moment, you can at least put forward two definitions, which are analogous to the source frame and detector frame masses that we are used to. So you could define a source frame eccentricity, meaning that you measure eccentricity a certain number of cycles before merger. And in this case, for convenience, we pick 13. So E13 cycles means I look at the signal, count 13 cycles before merger, and I have a measurement of the eccentricity right there. You can also define a detector frame eccentricity, which is the eccentricity whenever the source is emitting at 10 Hertz. Now, to meaningfully compare binaries, so sources with different orbital cycles in band, but the same SNR, such that the amplitude of the signal is the same, one can rescale the signal by basically introducing these prime quantities where you multiply them by a fudge factor. Now, this factor F is similar to redshifting to some extent, but don't think about the cosmological redshift. Just think about a rescaling of the signal. I mean, it could be greater than 1, whatever. Right. So in all this business, there are some technical details that I'm gonna skip. How do you actually count cycles? The eccentricity runs, our eccentricity runs are done with likelihood reweighting, which was put forward a few years ago. And then, of course, it's a 17-dimensional parameter space. So 2 more parameters if you throw eccentricity in the blender. And we are doing a bunch of runs in a huge parameter space. So that must be said. All right, so let's go through results now immediately. Right, so in this plot here, what I have is, so the number of cycles in band on the x-axis as a function of the bias factor, the log bias factor in favor of eccentricity. Up here means that the source is eccentric. Well, that I infer that the source is eccentric. And down here in the gray area means that the bias factor is too low, and I really cannot tell. The series of sources shown in these plots, the true values are, so there's some eccentricity, but they're all non-spinning. And we've done some series here where we vary both the source frame and the detector frame eccentricity. Right. So for these curves here, they are weekly or so increasing. We are keeping the source frame eccentricity fixed. And if you do that, if you keep the source frame eccentricity fixed and you increase the number of cycles, the detector frame eccentricity will increase, which explains how these bias factors go up relatively quickly or so. So for instance, in this series, it means that for a signal with, say, 7 or so orbital cycles in band, you can tell it's eccentric with a log bias factor of 20 or so. Crucially, something that is down here as a bias factor of like 0. And these vertical lines indicate some of the gravitational wave events. And 1905-21, the highly debated case is right here, where it's basically all bias factors are basically 0. These are the curve here, which has a different trend. That's a different series where we're actually keeping the detector frame eccentricity fixed, which means that as you increase the total number of cycles, the source frame eccentricity decreases, which implies that, well, but for this point that is basically 0 because the signal is so short, the bias factor goes down as with the number of cycles if you keep the source frame, the detector frame eccentricity fixed. Right. So in this series
to interrupt. You have 5 minutes left.
Yep, absolutely. So in this series here, we have eccentric but aligned injections. Don't bother with the green curves for now. That's a details that it's not crucial. So what we are seeing here is that the shapes of the markers here indicates whether spins are aligned, non-spinning, or anti-aligned. Now the key trend is that anti-aligned spins that are up here, the waveform is a bit longer because the two black holes they do a few more orbits before merger. That's called the orbital hang-up effect in GR, which for a fixed orbital number of cycles increases the distinguishability. So for anti-aligned spins, it's going to be a bit easier to tell whether a system is eccentric rather than precessing. Finally, this is the opposite case, where we are actually injecting quasi-circular precessing sources and try to recover with both precessing templates and an eccentric template. So now negative bias factor here means that the source is precessing, and I know, and I can tell it is, and I can tell that's the case. Now for this scenario, we actually found that the inclination of the binary is crucial. You do need, largish inclination before you actually see something. Secondly, the other key features here is, for instance, is very evident in this series here, where there's a steep drop up to, I don't know, 7, 8 or so orbital number of cycles, which for these specific binaries, that's about the length of a precession cycles, which confirms our intuition that if your signal is at least a precession cycle long, that's information that you can actually take out of the data. All right. So these three plots are these three subplots are actually in a single plot, and it's the only plot of the paper. So that's a one paper, one plot case. The conclusions here is that signals in general, the general trend here is that distinguishability increases with the length of the signal, which respects one's intuition. And crucially, 1905-21 is not long enough to say anything meaningful about whether the system is precessing or eccentric. That said, there isn't a genuine degeneracy between eccentricity and spin precession, because you can find favorable configurations where distinguishability is actually possible, even for relatively short signals. For a fixed detector frame eccentricity, the distinguishability increases with the number of cycles. It's going to be easier to discriminate eccentricity if spins are anti-aligned. That's because the waveform is a bit longer, and easier to confirm spin precession for large inclination, as long as you target at least one precession cycles in the signal. And this is all from me. Thanks.
Thanks a lot. Are there questions for Davide? Okay, while you think, I keep going asking my question. So what you're showing is, if you go back to the three plots, the one plot that is actually three plots. So every time, for example, eccentric non-spinning, you have injections that are eccentric and non-spinning, and your model. So I'm just wondering, why does this curves go up faster than in the plot just below? This is because you have to add some spin parameters to the PE while you do it. So non-spinning is only for the injections, or also on the PE?
Both. So
both. Okay. Every time.
Okay. So for each injection, we recover it twice. Once with a template that is precessing but quasi-circular, and then again we redo the run with the same signal for using a template that is eccentric but spin aligned, right? And then the goal here is to find the bias factor between the two runs. That's going to tell you which model is preferred, so which model better explains the data.
Okay, so we recover non-spinning injections better than anti-aligned, even though those are longer. That's
though with the not grain, but with the giant block of salt, that these are a bunch of runs in a 17-dimensional parameter space. So
Okay,
I mean,
sure. Yeah.
That's what it is. I mean, it was already computationally expensive to do this.
Sure.
So,
But so in these three plots you have, we never get them wrong. But worst case, we can't tell, right?
That's right.
Okay.
That's right. We didn't find a single case there where you get it wrong.
Okay. Oh, Simon has a question. Please, Simon, go ahead.
Hey, Davide. Yeah, nice work. So I was wondering, is this kind of some kind of cosmic conspiracy where, the fact that these most massive signals are the ones where it's hard to tell if they're precessing or eccentric, but astrophysically it might be the most massive ones where we might expect them to have these particular precession or eccentricity. They're formed in clusters or
I don't think it's a conspiracy though. It's just
or AGN or something.
Words, right?
So does this mean that we basically are doing this with LIGO and that we need to wait until like ET or something to do this?
Well, yeah, I don't think it's a conspiracy. So more massive signal means merger at lower frequencies and shorter signals. Right. So that if you have an astrophysical model that predicts eccentricity for a black hole of 80 solar masses, the only thing you can do to see it is push down the low sensitivity wall of the detector. Right. I don't think there's a way out of this.
So hopefully we can get something interesting already with better sensitivity in LIGO. Let's hope we don't have to wait all the way to.
No, we need a low mass. We need a low mass signal with precession or eccentricity signatures, right? That would be cool because there's many cycles, and then these things all becomes constrained.
That's my point,
So,
I guess.
Simon, please predict the low mass.
Binaries.
Please, Simon, predict the low mass signal with with the.
Okay, thanks. I just have one quick one, which is, you said we cannot do eccentric and precessing PE yet, but could we do injections? Would it make sense to make precessing and eccentric injections for precessing and eccentric system, and then try this code of yours? So you don't try to infer both, but you try to generate both and see how wrong we get it, or it wouldn't, or it's impossible.
Yeah, it requires some technical. There aren't waveform templates ready to use. One could possibly inject a numerical relativity simulation. One could inject an eccentric precessing NR run and try to recover it with the templates that we have. We haven't done it because NR injection requires a different machinery and so on. But
okay.
Sure.
I understand. Okay. Well, I don't see any other hands. So thanks a lot again. Davide, we can move to next presentation by Eliot. Our next speaker is Eliot Finch about identifying LISA verification binaries amongst the galactic population of double white dwarfs. So great, we see your slides and they're in full screen. So please go ahead.
Okay, yeah, thanks for having me. So I'm going to talk about some work I've done with a bunch of colleagues at Birmingham, including 3 summer students. So it's a study on LISA verification binaries. And I'll just kind of start by giving some numbers, which I think are useful to keep in mind. So LISA will be able to resolve about 10,000 of these compact binaries, the majority of which are double white dwarfs. And that's what I'm showing in the figure. This is the LISA noise curve, the instrumental noise curve, and each dot is a galactic binary. So these are essentially monochromatic sources. You should think of these as like spikes in frequency, but I'm just plotting them as dots for clarity. But it turns out this is only like the tip of the iceberg with the number of these sources. In the entire galaxy, we estimate there's about 10 to the 7 of these in total. LISA can't resolve all of them. Instead, they kind of merge together, they blur together, and you're left with this confusion noise, essentially, like this addition to the noise curve from all of these sources. These numbers are kind of estimates from population synthesis. We've not actually observed this many sources in electromagnetic radiation, but we have observed a subset of them. And of those which are in this 10,000 resolvable there's about 25 we found in this study that we know exist in electromagnetic radiation, and we know that LISA will be able to see. And these are the verification binaries, which I've shown with the red dots. This is just an illustration. So the study, we found this number 25. So I'm going to talk about how we arrived at that number. The process is fairly straightforward. Basically, telescope surveys are continuously discovering these compact binaries and measure things like the orbital period, masses, and distance with some error bars. And I should say we made use of this very useful resource Thomas Kupfer and others put together. It's available online. It's a table of verification binary candidates and all of their EM properties. So then basically you can just transform these parameters into a grav wave signal with these various relationships. As I said, these are essentially monochromatic sources, so it's kind of like a sine wave that you get out. But the point is we can predict the gravitational wave signal. Then with that, we have code at Birmingham called Balrog, which we can simulate a LISA data stream with, basically. So processes EM parameters, GW waveform. We simulate some LISA data with that waveform included, and that allows us to do parameter estimation. We can then look at that artificial data and perform Bayesian inference to see how well we can recover this signal in the data. So we did that, and you get a bunch of corner plots. And here I'm just kind of summarizing the results you get with LISA. So for each of these GW parameters, you recover them with some uncertainty, which is what's being shown here. And this is also how we arrive at that 25 number, because we can see from all of the candidates we inject, we can work out the SNR over time, and our detection criteria is an SNR greater than 6 over 4 years, of which these 25 satisfy. So all of this is in the paper. We also have a data release with all of the posterior samples. But, and although this was done with like the full LISA state-of-the-art treatment and Bayesian inference, there's still some assumptions going on here. Namely, each VB was injected into a zero noise realization, and they're analyzed in isolation of any other source. Also, the confusion noise only enters as this like analytical addition to the noise curve, which is fine, but it's an approximation. So what we wanted to do was to perform a more realistic analysis, basically to see how well these assumptions hold. So what I mean by that is, well, we take one of these sources, V803CEN, which is like a 30 SNR thing after 4 years, with around 1 millihertz. And basically we generate another LISA data instance with this source included, which also includes an instrumental noise realization. But now, instead of just having an analytical confusion noise curve, we're going to actually take a mock galaxy of double white dwarfs, and we're going to add that to the data, basically. So that's going to, all of those are the signals from the mock galaxy are going to constitute the confusion noise, as well as these other like 10,000 above threshold sources, which we're going to need to model, even though we don't know that they're in advance. So the data analysis problem looks something like this now. In frequency domain, I said these things are like essentially spikes. They're monochromatic. So if we look at our verification binary in red, basically we have that in the data, but now we have a bunch of other sources which we don't know about in advance, but we're going to need to do something about. And we use this mock galaxy from Wilhelm. As I'll explain, we don't inject all 10 to the 7 because in reality, the way we analyze this data is to look at a narrow range of frequencies surrounding the source. So we can filter the galaxy for sources within that frequency range. So we do that, and it turns out we find there's 2 sources from that mock galaxy that are above our SNR threshold of 6. So what that means, these are kind of 2 sources that are in that 10,000 number, which we don't know about in advance. So they're not verification binaries, but they're loud enough to actually resolve with LISA. So we're going to need to model them. All of the other sources are what add up to make this confusion foreground, which we're also going to need to model somehow. There's one subtlety, which is that we take sources surrounding our analysis data so that we don't lose any power at the edge of the band we're analyzing, just a detail. So now the solid black curve is our like confusion level. We can look at this in a sky map. So what I'm showing here is each black dot is one of these sources that are making up this confusion noise. It turns out there's about 200 of them surrounding this verification binary. Also shown are the two above threshold sources. We're also showing here the actual sky map from a PE run, which I'll talk more about in the following slides. But good news, you can find these things on the sky with some uncertainty. And then finally you have the verification binary, which in this analysis, since we know the sky position, we fix that in the PE. So there's no sky uncertainty here. And just to help kind of guide the eye in, the color bar is showing, sorry about that. The color bar is showing the actual density of white dwarfs in the entire galaxy, that 10 to the 7. Okay, so first of all, we're going to address these 200 or so below threshold sources, which constitute the confusion noise. To deal with them, we introduce a new parameter, delta, which is going to rescale our instrumental noise curve. So S is the PSD, essentially. It's labeled by alpha, which has 3 values, A, E, and T. This is basically the 3 data streams you get from LISA. A and E are where the signal is expected to appear. T is like a noise channel. But the point is, for each of these channels, each of these data streams, you can essentially just rescale the noise curve like this. And on the left, we're showing posteriors on delta in each channel. And what we find is this thing peaks around 4 or 5, meaning all of these below threshold sources are summing up to effectively raise the noise level by a factor of 5 or 6. But this looks good. We're capturing some excess power here with this delta parameter, and it seems to be doing the job. Okay. Then this is the posteriors on the above threshold sources. So the verification binary of SNR30, and then each of the 2 above threshold sources. I already showed the sky map for these. Now I'm showing amplitude, inclination, and the GW frequency. Kind of the main takeaway here is that we recover the VB parameters consistently with what was injected. So that's a good thing. We've accounted for all of the possible biases. And we also find that the uncertainty on these parameters is comparable to what we found with the more simplified analysis in that big table at the start. So everything seems to work out. GP2 also looks good. Everything is consistent with what was injected. GP1 is showing bias in the inclination and amplitude. So we have some thoughts on this, but basically it comes down to the fact that in your confusion noise, it's not perfectly modeled by an adjustment to the noise curve. There's going to be some sources which are just below threshold, which are going to interfere with the analysis of these guys and lead to biases. So it's something that's good to be aware of, that it's a tricky problem.
Sorry to interrupt, you have 5 minutes left.
That's fine. I'm near the end actually. So the final thing is that in reality, we won't actually know the number of above threshold sources, because these are EM dark in a sense. They're among those 10,000 which we don't know about in advance. One way to deal with that is do a series of runs where you search for different numbers of additional sources. So in our case, it was 2. The the GP1 and GP2. But we can repeat the analysis, as I said, for different numbers, and then you can compare model evidences, basically, to get a base factor. And when we do it with our mock data, we find that it peaks with 2, which is in line with our expectations. So this is one approach for dealing with the problem of not knowing how many additional sources you need to model. So I'll just wrap up, but I just want to point out that, well, I'll just summarize quickly everything. So first bullet point is just saying we find and characterize these 25 VBs. In the paper, we also look at things like how prior knowledge of EM observations, prior knowledge from the EM observations allow us to improve our inference. For example, it allows sources to be detected earlier if you use informative priors. And in particular, we find it's the inclination that helps out the most. All of that is in the paper. And then finally, we did this realistic analysis with the chosen VB, where we injected it into the synthetic population, analyzed the small frequency range, accounted for all of the other sources within that frequency range, and we did a successful inference. Yeah, so I think I can end it there. So thank you for listening.
Thanks a lot. Are there questions to Eliot? Okay, let's wait for hands to come up. Meanwhile, I'm discovering that Lisa has a lot of funny names in the data sets and also in the codes that you use. So I was just wondering, I'm not expert at all, but so when you say you do PE analysis, so we've heard before trying to use VLB as a code for PE analysis in Lisa. What did you use in practice yourself? This is like a package or a handmade?
Yeah, so it's not public yet, but I guess the package is this code base called Balrog, which handles the kind of things that Bilby would handle, like projecting signals onto Lisa, simulating noise. Sampling is done with Nesai in most cases, which you can change in this Balrog code package, much like you can in Bilby. Yeah, we hope one day this will become public and something people can use to simulate Lisa. I guess it's analogous to Bilby, I guess, in some ways.
Nice. Okay, yes, and absolutely. Being public is the best way for your code to be used. So
yeah,
okay.
One day.
And then I have a question on your, I think slide 17, but this was a question I had before because you say, okay, in this case, we have 2 sources that might be overlapping with our verification binary. And then you said, okay, but we don't know how many we have, like that are above threshold. And so you said we did or maybe the slide after, you talk about a more realistic analysis, but I'm not sure I got it. So did you consider an unknown number of sources? So you, for example, overlap different above threshold sources, but then you don't know how many there are in your analysis, and you try to see if you recover the correct number, or maybe I'm so you did that.
That's the idea. I mean, the thing here is we generated the mock galaxy and we used that, right? But in reality, we won't have that. It'll be similar, but it's like we used one instance of the galaxy, but in reality it'll be different because we don't actually know all of the EM dark sources, of course. So yeah, in actual reality, we'll do something like this, but we'll need to determine the above threshold sources, like just in some methods, which was where the base factor came in, because you can repeat the whole analysis just with different numbers of additional sources. So I could explain this a little more. So for 0, it's like you take that data and you just search for the verification binary. So you only have one, you only have the red. But it turns out if you include one extra source, the model evidence goes up a lot, and so that's an indication that there's something in the another VB in the data, another double white dwarf in the data, which you need to model. But then in line with our expectations, if you include 2, this thing goes up even more. less so, but it does, and it peaks. And then for 3, it doesn't go down much, but at this point, it's like a small Occam penalty, basically. It's not doing any worse, but you don't need to include 3. So that's basically the idea. It's the number of contours on this.
I understand. Yeah. So at some point, I guess one needs to quantify, do we trust? Then imagine we have a data set that we don't know what's inside. Maybe based on a simulation, one can state whether we trust or not the number of sources that are above threshold that we find with our procedure, I guess.
Yeah, for
making
sure.
That, okay. Okay, thank you. So I don't see any hand. There is a, okay. Hi, Miaoxin. I think Thankful is taking care of your Zoom related question. So thanks again, Eliot. We can move to next presentation. So this is by Lucy Thomas. Hi again, Lucy. We tried. Okay, hi. So Lucy is going to talk about constraining spin precession in the black hole binary population with next generation ground-based gravitational wave detectors. So please go ahead.
Thank you. So hello, everyone. My name is Lucy, and yeah, I'll be talking about constraining spin precession in the population of black hole binaries with next generation ground-based interferometers. And this is a piece of work that I'm currently doing with my collaborators here at the University of Birmingham in the UK. Sorry. So I'm sure that this explanation is probably wasted on many people here who will know exactly what I'm talking about, but just to check that we're all on the same page, what is spin precession? Why is it important? So spin precession in a black hole binary occurs when the black hole spins are misaligned with the orbital angular momentum in the inspiral. So I've got a little picture here in the top right of the slide. The purple disk is the orbital plane of the binary, and on the left-hand side of this little picture, the 2 black hole spins, the purple arrows are aligned and anti-aligned with the orbital angular momentum in blue. So that orbital plane, the purple disk, stays fixed throughout the inspiral. But on the right-hand side, the 2 spins are not aligned with that blue arrow, the orbital angular momentum. And so the purple disk, the orbital plane, and also the spins precess around. And this has implications for the gravitational waveform and for the signal that we see. And precession is important, and it's important to measure because it breaks parameter degeneracies in the individual binary parameter estimation. So when we're trying to measure the properties of these binaries, we can use that precession and the complexity that it brings into the waveform to then break parameter degeneracies. An example I've shown here on the bottom right of the slide is from a recent paper where we're trying to measure neutron star black hole masses and parameters and spins here. So we've got the mass ratio on the x-axis and chi effective, which is an effective spin parameter on the y-axis. And if you include precession, then you break this sort of parameter degeneracy banana in the solid lines versus the dotted lines, which don't include precession and when recovering the mass ratio and chi effective. And precession is also a really important tracer for the formation channel for the binary black holes, because certain formation scenarios, we much more expect to see precession in a binary versus others. So how are we doing with measuring spin precession currently in our population of black holes? So there's some possibly promising precessing events. There's 2 notable ones that I've put here, which Davide also talked about earlier. So one is GW190521, which was this very heavy short signal, but that short signal has really obfuscated the interpretation of this event as a precessing quasi-circular binary black hole, as Davide said earlier. And the second one is this GW200129. And this event, depending on who you ask, is precessing or not. It's complicated by different waveform models and systematics and also data quality issues. So I've put here, the plot on the slide is from this paper by Ethan Payne et al. From 2022. And it's showing that a lot of the power and a lot of the information about whether or not this is precessing is coming from one detector, Livingston, in the blue contours, but there was a glitch in Livingston. And so this interpretation then massively depends on how you deglitch the data. So it's unambiguous, so it's ambiguous to just interpret this as definitely a precessing binary black hole merger. There is also evidence of precession occurring at the level of the population of black holes. We're starting to see evidence for that, such as in the GWTC3 population paper. but no unambiguous detection of precession in a single binary black hole event has so far been detected. So how might this change in the future? Well, the next generation of ground-based detectors are expected to have much better low frequency sensitivity. I've put a plot here of the PSDs on the left-hand side, and compared to the LIGO A+ and the advanced Virgo design sensitivity curve in sort of teal and purple, we expect to see roughly a factor of 10 improvement at 20 Hertz, which is that dotted gray vertical line. And this will allow for higher mass and redshift observations, and also a lot more of them. But the exact minimum frequency of these next generation detectors, Einstein Telescope and Cosmic Explorer, is uncertain at the moment. Longer signals and lower frequency cutoff will mean better spin constraints because we expect it to scale with the SNR and the signal length. But how much does that uncertain minimum frequency actually affect our ability to constrain precession in binary black holes in these future networks? That's sort of the question that we're asking with this work. So let's think about this in terms of just a single event, 1905-21. So what we did to sort of get a picture of what was going on here, we injected a 1905-21 like binary with zero noise with the waveform model IMR Phenomics PHM into a next generation ground-based detector network. And you can see the network that we used up in the top right of the screen with that little map. So we've got 2 A+ detectors and 1 Einstein telescope. We then varied the minimum frequency in the Einstein telescope between 20 Hertz, 10 Hertz, and 5 Hertz, depending on what the low frequency would be in that detector. And we find in this corner plot I've got here that there is a much more precise spin parameter recovery with that lower frequency. So you can see that the contours go from these massive purple ones at 20 Hertz to smaller teal ones at 10, and then 5 Hertz is very, very small in orange, and they much better recover the true parameters because of this longer signal that we would observe in band with 5 Hertz and more accumulated SNR. But then we also wanted to know, well, what if it's not just SNR that's happening? What if actually the longer signal length and more precession cycles observed in this processing 1905-21 that we ejected are both playing a role in the improvement that we're seeing? So here on the corner plot, you're now seeing the same binary, but we changed the distance of the binary at each value of minimum frequency so that the SNR was the same across all 3 of the injections that I'm showing here. And actually, there is a little bit of improvement. Even with the same SNR, we're still recovering slightly better spin parameters. The difference is small, but it's there. So actually, we're showing here that although increasing the SNR with the lower frequency has the biggest effect on how much we can improve our spin measurements, also actually the long duration of the signal does play a small role. So what about a population of black hole binaries? So we drew a population of 20 black hole binaries, quite a small number because that's a lot of parameter estimation to do because you need to do 3 for each binary. We drew this population from the population that was inferred from GWTC3. And here in the bottom left, I'm showing the distribution of total mass in the detector frame and also of chi-p, the processing spin. So we've got quite a range of both. The detector network that we used is there in the top right-hand side. So now we're actually using advanced Virgo. We're using 1 Livingston A+ detector and 1 3G Cosmic Explorer. Again, we use the same waveform model to inject and recover. And we varied the minimum frequency for each of these 20 binaries. So for 20 binaries, we have 3 different minimum frequencies, which is a total of 60 injection and recoveries. So just to really hammer home what we're doing, we draw our population from GWTC3, the population inferred from GWTC3, sorry. Then for each of these 20 binaries, we do 3 different individual parameter estimations with Bilby, 1 for 20 Hertz, 1 for 10 Hertz, 1 for 5 Hertz. So that's 60 in total. And then for each of those 3 populations, so we have a 20 Hertz population, a 10 Hertz and a 5 Hertz, we then perform population hyperparameter estimation. And we would naively expect that we'd better be able to constrain the population hyperparameters and actually the spin distributions across the population with lower frequency. So 20 Hertz is good constraints, 10 Hertz is better, and 5 Hertz is best. Okay, so actually what happened? Some results. So in the corner plot on the left, I'm just showing a representative example for one of the 20 binaries. And exactly like we saw with 1905-21, the lower frequency that you have in Cosmic Explorer, the better you constrain your spin parameters. That's expected. on the right-hand side, I'm showing the 90% posterior widths for my 20 binaries for chi-effective. I've sort of normalized them so that I took away the actual injected value so that they would all hopefully nicely lie around the 0 line. But you can just think of these bands as the 90% credible interval contours and the width of those on chi-effective. So again, really nicely, we can see that the 90% credible intervals are shrinking with low frequency. So the orange one, 20 hertz is the widest, and then purple 10 hertz and 5 hertz is green. So now that we've seen that for individual events, you get better constraints on the spins, how does this actually affect the accuracy to which you can constrain your population spin distribution? So although you don't need to, we are doing population inference with population hypermodels. So we're doing parameterized population inference. And we chose 2 different hypermodels for our spin distributions. One called the effective spin hypermodel here is where you model your effective spins chi-effective and chi-p as a bivariate Gaussian. And it's parameterized by the means and standard deviations of the Gaussian and a correlation parameter rho. So 5 different parameters. And the second model that we used is where you parameterize your spin magnitudes, each chi1 and chi2 by independent beta distributions. So then you have 2 shape parameters, alpha and beta for each of chi1 and chi2. We didn't consider a spin tilts hypermodel because there is a very small number of binaries in our population because we have to do 3 times the number of parameter estimations. And we did try, but we found that even with 20 hertz, we didn't really constrain any spin tilts. Even with 5 hertz, we didn't really constrain any spin tilt information with this number of binaries. And just a quick note to say that actually, because we've only got 20 binaries, the population hyperparameters that we're actually injecting do not exactly reflect the underlying population of GWTC3. So in green, you can see the population inferred from GWTC3 that we actually drew from the predictive posterior distributions. In orange, you can see the sort of best fit with these hypermodels to that green line. And notably for chi-p, the orange bivariate Gaussian distribution does not really well fit the underlying population of GWTC3, and I will come back to this point later. And then purple, you can see the distribution of the actual 20 binaries that we injected. So in each of these 3 spin parameters, it is a little bit different, and I will show results that have the true values as being the population of 20 binaries that we did actually inject.
So sorry to interrupt, you have 5 minutes left.
Lovely, thank you. So some population results then for the effective spins. So the black lines and dots on this corner plot are the results for the actual 20 binaries that we injected. So we can think of those as our true values. And nicely here, we can see that a lower minimum frequency does lead to better recovery of the injected population parameters, that the orange and green are better recovering for, I think, all of our parameters, or maybe at least all except one, the population hyperparameters that we actually did inject. The 20 hertz results that you see here are driven by the priors of the individual event parameter estimations, which I can talk about a little bit more if anyone is interested. But we find that we're actually very sensitive to the actual population we injected in this hypermodel, the 20 binaries. And because we saw before that the green and the orange line for chi-p, the bivariate Gaussian, didn't actually well reflect the underlying population from GWTC3, actually this population hypermodel at these high SNRs might not be representative enough to constrain the population very well. If you're trying to constrain the population with a hypermodel that doesn't fit the actual true underlying population, you're going to run into issues at high SNRs and with large numbers of binaries. And finally, the results for our spin magnitudes distribution, which did fit the underlying population a lot better. Again, lower minimum frequency leads to better recovery of the injected population. The 20 hertz isn't sufficient to recover the population hyperparameters at 90% confidence level. The true values for many of these hyperparameters lies outside the 90% for the purple contours. And this hypermodel is more representative, so we can trust our measurements more in some sense for this hypermodel. Okay, so that's everything. Thank you. To conclude, that we don't have an unambiguous detection of precession in a binary black hole merger yet. Next generation interferometers will be able to give us more accurate spin measurements, but it does depend upon the low frequency sensitivity of those instruments. We've shown that we can better constrain the population spin distributions with a lower minimum frequency, even with the same number of 20 binaries. And finally, a simple bivariate Gaussian might not be sufficient to constrain the effective spins. So we really, really need representative population hypermodels to constrain our spin distribution. Thank you very much.
Okay, thanks a lot. Are there questions for Lucy? Okay, let's wait if people raise their hand. Meanwhile, I'm very interested in what you say about, we need a representative population hypermodel, because of course, in this case, we might know what is a good representative model, but in real life, I'm not sure how would we go about it. I don't know if you have any suggestion on that, or okay, go ahead, please.
No, I mean, you raise a good point, and I don't necessarily have a suggestion, but just making sure that we include enough freedom into our population hypermodels is a good thing. So while small numbers of parameters that really do parameterize the distributions we're seeing, we need to. I mean, I'm of the opinion that running with both models that have a small number of parameters and also non-parametric models that have the flexibility to really pick out the features that we're trying to measure, a mixture of both of these things together, and a variety of population models, just using one hypermodel for your population at once is maybe not a good idea. You want to do cross checks, and you want to make sure that really you're measuring the features that are there in the data.
Yeah, absolutely. So this was also, we made similar points in other presentations, but yeah, that's a good point. And then after Davide's presentation, I cannot help asking, so we've seen there is a degeneracy between precession and other parameters like eccentricity. Did you at all think about it, or this is really, focusing on, but it's okay. I mean, one has to start somewhere, but I was wondering if you thought about it.
Yeah, we haven't thought about it in this work. I think Davide said earlier that, so we're not doing numerical relativity injections here. We're doing waveform injections because that's really the fastest thing that we could do, and for the most number of binaries. And so we don't have any waveform models at the moment that really do include eccentricity and precession that we could inject to then measure. So we're just looking at precession in this work. But good one for the future.
Yeah, right. Yeah, there are many things on which the showstoppers are still technical, which is, in some cases a good news, but still a lot of work for some people. Okay, I don't see any question for Lucy. Please raise your hand if I missed any, nothing on the chat. So thanks again, and we can move to the next speaker. And the last speaker of the session, this is Miaoxin Liu, and the talk is on improving the scalability of Gaussian process error marginalization in gravitational wave inference. Go ahead.
Okay, thank you. So my topic is improving the scalability of Gaussian process error marginalization in gravitational wave inference. So I will first introduce the background, then the base model in previous work, and our improvements in this work and results. So in many contexts of gravitational wave inference, we have accurate templates, but they are computationally expensive. So people will use approximate waveform, which is cheap, but it has waveform difference against accurate templates. And this can lead to bias in parameter estimation, which is theoretical error. If we can have a prior distribution of waveform difference, then we can mitigate the theoretical error in likelihood. In this work, we choose extreme mass ratio in spiral waveform as an example because its intrinsic information content and computational complexity optimize the most difficulties that prohibit the usage of Gaussian process regression in higher dimensionality. The accurate signals is chosen as 5PNAAK in fast memory waveforms package because it's the most efficient, currently the most efficient option for fully generic curve waveform. And the approximate template is modified from 5 p.m. AEK by interpolating the trajectories between 5 p.m. and 4 p.m. This is the semi-lattice vector, eccentricity, and cosine of inclination. The coefficient is chosen as 0.001 in this work, and we will estimate the 6 intrinsic parameter of Emery, and the waveform duration is half-year and will plunge. For Gaussian process regression GPR, we will feed Gaussian process to waveform arrows. Then the process will tell us the waveform difference prior distribution. Then the prior distribution can be marginalized in likelihood. Here we define the inner products, signal to noise ratio, and overlap between two waveforms. Note that the overlap between accurate waveform and approximate waveform in this work is equal to 0.84. And here is the standard likelihood. If we express H in terms of approximate waveform and waveform difference, then we can marginalize the waveform difference by this formula. If the waveform difference of a Gaussian distribution, then this integration can be done analytically, and we arrive this formula. This formula will be further explained in following slides, which is the marginalized likelihood. So for a simple case of GPR, here we can have 9 waveform, and the red dots can be the first data point, second data points, or last data point of the waveforms. And Y is the waveform magnitude, X is the source parameters. We can feed Gaussian process to this 1D function, and it has 9 samples in training sets. Assuming the samples are correlated with each other and they obey a 9D Gaussian distribution, then we may want to know the correlation between those points. In GPR, people use metric to describe the distance in parameter space. Then the distance in parameter space will go into kernel function, and the kernel function also has some kernel parameters. The value of kernel functions is assumed as the correlation between the training set points, and the metric and kernel parameters is the parameters to be tuned in training stage. With the kernel function, we can have the covariance matrix for training sets just to calculate the kernel function pairwise in training sets. And the training set is a vector, and its components is also vectors. This is a waveform difference in training sets, and this is the average of the training sets. Note that both of them are vectors. Assuming the waveform difference obey Gaussian process, then we can have our probability density to observe the training set. During training, we want to maximize it. So its roles is like the loss function. And we can, since this part is a scalar, we can write the trace ahead of it. And because the trace AB equal to trace BA, VT can be moved to this place. And VVT is the M matrix, which is defined as this way, just to calculate the inner products of waveform difference pairwise in training sets. So we can write VKV in this way, the trace KM, which is more convenient to compute. With the covariance between training points and test point itself, we can calculate the expectation and variance of the waveform difference in test points. Combine the expectation with the approximate waveform, then we can have our GPR waveform. The GPR waveform will go into the marginalized likelihood, and there are also GPR variance. For training set construction in previous work, they calculate the feature information matrix. Then its associated covariance hyperellipse semi-principal axis is taken as the base of the grid, and the training set points will be sampled on this grid. But this method is not used in this work. For the first drawback of the grid, it weighs a lot of points in low likelihood region. In 2D, draw an ellipse, inscribe a rectangular, there are 4 corner region. And the four corner regions is the low likelihood region. When dimensionality more than 6, the corner region will be more than 92% of the hypercube. So for our mature model, the training set boundaries is hyperellipse. Also, since grid training set is more regular than random sample training sets, it has less entropy and contains less information. So in this work, our random method is letting hypercube sampling LHS. In 2D, LHS will sample points not at the same column and not at the same row. So these two can be the samples from LHS in 2D. In this way, LHS keep distance between points while randomly sampled. In this figure, the green is the grid training set points, and its numbers is 4 to the 6, and the yellow points is the LHS points. It has the same boundary and same point numbers as the grid. We verify that under same metric, the grid training set has less entropy than LHS training sets, and the training results on grid is very bad. So in this work, we will use LHS. During training in this work, the KMs is calculated by conjugate gradient method. In this way, we avoid matrix inversion of K, so such that its scalability is better. And for the training set size of 4096, it takes 3.5 seconds for 1 iteration and 200 iterations to converge. At evaluation stage, since the KV and Ks is not changed with the test points, we can pre-compute them and don't need to calculate more times. For test points, it takes 0.01 second on GPU and 0.1 second on CPU for the calculation of expectation and GPR variance. For our mature model used to do parameter estimation, its shape is its boundaries is a hyperellipse that inscribe the hypercube boundary of grid, and we chose the points within such boundary as 1611. When there are noise presented in signal, we can write the expectation of Loin likelihood in this way. The N is the noise power. When the noise power is much larger than the inner product, then it may dominate the likelihood via the variance. So a natural way to mitigate this is to add this term at this place, such that it will become a constant term in the Loin likelihood. But the problem is...
Sorry to interrupt, you have 5 minutes left.
Okay, thank you. So the problem is how to estimate the noise power M. In this work, we apply iterative inference. So for our first GPR model, its center of training sets is the best viewpoint of approximate waveform. And we will train on these training sets and estimate the noise power by this way. The X is the signal, this is the approximate waveform and its best viewpoint. And with the first GPR model, we can have our second GPR model. The center eccentricity is the best viewpoint of first GPR model, and we will train on this new training set again and estimate the noise power by this formula. This is the accurate waveform. So for our results of the first GPR model, those are 3 sigma region, and the greens is the approximate likelihood. It exclude the true value at 3 sigma region, and the blues is the accurate likelihood. The orange is the first GPR likelihood. It contains the true value already. For the second GPR likelihood, it matched the accurate likelihood very well. To sum up, the motivation of GPRs is to mitigate the theoretical error. And in this work, we extend the base model to higher dimensionality. Our main improvement lies in we use LHS training sets with hyper-ellipse boundary, and we use a new marginalized likelihood adapted to noise. Our result shows this method's viability for more realistic gravitational wave applications. And our paper is submitted to archive already. That's all, thank you.
Thanks a lot. Are there questions? Please raise your hand or write on the chat. Meanwhile, I take the chance to ask mine. So I'm not sure maybe I missed something, but your LHS, a new method compared to the grid, like a classic one, let's say, is it only less, is it like more optimal computationally, but in terms of accuracy, the two are similar? I'm not sure I got it. Is it just a, computationally better, a smarter method, or do you gain also in accuracy somehow?
Do you mean the comparison in this slide?
Yeah.
Yeah, so to strike a fair comparison, the boundary of the random sample training sets is same as the grid training sets, and the white numbers is also same. So on this way, we calculate the entropy of these two training sets, and the entropy definition is in our paper, but I don't have time to introduce the derivation for entropy here. And also the expectation, the more description about how the grid training set fails in training stage is described in paper.
Okay, I see.
Yeah.
And I have another comment on your very last slides where you were showing how the likelihood in the end was really matching the accurate one. Yeah, that is very nice to see, visually on this example. But I was wondering, so ideally, I guess, one would like to make like a large scale simulation and then show, the coverage of such methods and say, 90% of the cases I'm within the 90%. So I was wondering if you plan to do that, or if this is feasible technically, or if you think it's a good idea quantitatively.
Firstly, our method is very local. So we aim to do precise estimation rather than a full space search. And our method will first use the approximate waveform to locate rough region of the likelihood. Then we use then we can take it as the center of training sets and search around this region.
Okay, I see. I guess what I'm saying is this is one example. Yeah. Are you sure this would work in any example, or how sure are you of the performance in a generic case? You see what I mean? Like, did you try to generate 1,000 of them and then see how it behaves? Or maybe this is not a good way forward. It's a question.
Yeah, but for if I want to calculate many samples, I will have to calculate a lot of accurate likelihood to compare. But for this one accurate likelihood, it already takes about 1 million cores for the accurate waveform. So it's very computationally expensive.
I understand.
And yeah, and I think the whether it works mainly depends on the overlap and the waveform complexity. The overlap in this work between the accurate waveform and approximate waveforms is 0.84.
Yes, you mentioned this. Also, this number was chosen for a reason, or just it's a reasonable number, or there are any constraints that led you to this specific value?
This is randomly chosen.
Okay, I see. Okay, well, thanks a lot. Let me check again. I don't see any other hand up, and I don't see questions on the chat. So let me ask one last call for any questions for any of the speaker or any general comment. Okay, it doesn't seem so. So thanks a lot, Miaoxin. Thanks to all the speakers and all the people attending the session. This was very interesting, and especially thankful for your help. I think we can close the session, but thankful. Do you confirm?
Yep, that's correct. Thank you so much,
Okay.
Fiona,
Thanks a lot, everybody.